Hey everyone, welcome back and let's write some more neat code today. So it's been a while for me, sorry I've been pretty busy, but let's today solve LeetCode 42, trapping rainwater. So we're given an integer array representing the heights of certain elevations or whatever, right? So it's a one-dimensional array. The first value is 0, meaning a height of 0, so that's over here. The next value is 1, so that means a height of 1. Some have heights of 2. This one has a height of 2. This one has a height of 3, right? And so given this entire structure, we basically want to know what's the maximum amount of rainwater could this structure trap, right? Given an unlimited amount of rain. So you can see this is 1 unit right over here. This is roughly 4 units, right? 1, 2, 3, 4. And then this is another one, right? So when you count all of those, you get a total of 6 squares, right? So the output is 6. This can trap a maximum of 6 blocks of water. So with a picture, it's pretty easy, but how do you know, right? Like what's the algorithm to determine how much each position could trap, right? Like, for example, this position is the first one, right? So there's no boundary on the left of it, right? So no matter how much water we would add over here, it would all just spill to the left. And the same is true for this position, right? No matter how much water we put on top of here, even though there's a right boundary over here, right, there's nothing on the left of it. So all the water is just going to spill out to the left, so it's not going to trap any water. But you can see in the third position, we are able to trap exactly 1 block of water. So what's the algorithm to determine why is it 1, right? Because we care about the height, because we want to know how much water. And it's actually pretty simple, right? Take a look. So here we have 1 block of water. What if I added a second block of water? Well, we can see that there is a boundary on the right. This is good, right? But what about the left side? There's no boundary over here, right? Meaning any water I add is just going to spill out. The boundary only has a height of 1. So we're seeing that the height on the left is 1, the height on the right is 2. So we need to take the minimum of that. We need to take the minimum of 1 and 2 because that is our bottleneck. That is what's determining exactly how much water we are able to trap per position, right? For every single position, we need the max height on the left and the max height on the right, left and right, and then we need to take the minimum of those two. Let's take a look at this position. Clearly we can't trap any water here, but why exactly is that the case? Well, when you look at the right position, right, in the entire right section, the maximum height is a 3, right? So that's good, 3 here. What's the maximum height on the left side? It's a 1, right? This position is a 2. If we take the minimum of 1 and 3, we get 1. So that's our boundary. That doesn't mean we can trap any water here. We can trap 0 water here. The reason is because the actual calculation is we're going to take the minimum of the maximum left height and the maximum right height. We're going to take the minimum of those two, and we're going to take the height that we're currently at, right? So let's say h of the index I that we're at. So this is the equation we're going to use to determine at every single position I, let's say this is our I position, right? So you can see I is in this equation. This is going to determine how much water we can trap in position I. So we know the minimum of the max of the left and right, right? Because the left was 1, the right was 3. The minimum of those is just going to be 1. And h of I, so the height at position I is 2 over here, right? 2. So we're going to take 1 minus 2. That's actually going to give us a negative number, right? That's going to give us negative 1. But we know we can't trap negative water, right? So we're always going to round up. We're never going to use negative numbers because it doesn't really make sense to trap negative water over here. So really, since the solution is negative, that really means that we can trap 0 water in this position. But let's just move to a couple more positions before you probably get the idea. So over here, right? In this position, the height is 1, right? And the max height on the left is 2. The max height on the right is 3 again, right? So we take the minimum of 2 and 3, so we're going to get 2, right? 2 is the minimum. And height of I is 1, right? The height at this position is 1. So that means we can trap exactly 1 water in this position, right? Clearly that is the case, right? We're trapping 1 unit of water. And basically, if you did this exact same calculation for every single position, including this position, you'd get the appropriate water count. So this position would give us 2 units of water. This is going to give us 1. These are going to give us 0. This is going to give us 1. And the rest are going to give us 0 water that we can trap. Once we take the sum of all of those, we are going to get our answer 6. So now let me actually show you the efficient ways to solve this problem. Okay. Hey everyone, welcome to negative water, right? So we're always going to round up. We're never going to use negative numbers because it doesn't really make sense to trap negative water over here. So really, since the solution is negative, that really solve this problem. Okay, so I'm going to show you two different ways to solve this problem. Both of the solutions are linear time solutions, right? So big O of n is going to be the time complexity of the solution, but the first solution I show you is going to actually require big O(n) of memory as well. There's an actual optimization you can do with 2 pointers to reduce the memory from linear memory, big O of n, to constant memory. So I'm going to show you both of the solutions, and it's actually not a lot of code. The code is actually pretty easy. Since for every single position, right, to know how much water we can trap at index I, we need to know what's the max left and right height of every single position, right? So for this position, the max on the left is going to be 2 right over here, and the max on the right is going to be 3 right over here, right? So we're going to need to be doing that calculation a lot. So we can actually make an array and then store that calculation for us so that we only have to do it a single time each. So first we can scan through the array, right? Just go iterate through the entire array, calculating every single max left position, meaning for this position, what's the max height on the left of it? Well, there aren't any heights on the left of it, so it's going to be 0. What's the max height of this? Well, the max height is 0, right? That's the only height that came before it. What's the max height on the left of this? Well, it's a 1, right? So we can do this in linear time, big O of n time. So I'm just going to do that, right? What's the max height on the left of this? 1. Max height on the left of this. We have a new max, it's 2, right? We just keep track of what the current max is so far. Right now it's 2, 2. We got a new height, a new maximum, that's 3. So now 3 is going to be the max left height for the remainder of these, right? So we calculated the max left height. We can actually calculate the max right height pretty easily as well when we iterate through this in reverse order, right? We go from right to left. So initially the max right height is 0 because there's nothing on the right of this. Next it's going to be 1. Now it's going to be 2. And now we got to a 3, so the max right height for the remainder of this is just going to be 3. And remember, we actually need to take the minimum of the max left and the max right for every single position, right? So for this position, we want the minimum of these two values. For this position, right, 0, we want the minimum of these two values, right? Because the minimum is going to help us determine how much water we can trap in this position, right? And clearly, we can actually find the minimum of these two arrays as well in linear time. So here, the minimum is 0, minimum is 0, minimum is 1, 1, 2, 2, 1, and 0. And so now for every single position, we're going to determine how much water we can trap. And we can do that, remember, with our calculation, we can take the minimum of the left and the right and subtract from it the height at position I, right? And we're always going to round up. We always want it to be greater than or equal to 0. And then we can add the sum of all of those values and then get the total water that we can trap. So in this position, we have 0 minus 0 minus 0, right? So here, the amount of water we can trap is 0. Here we have 0 minus 1. That's going to be negative 1, but we don't count negatives, so the amount of water we can trap here is 0. Here we have 1 minus 0, the height at this position, so we can actually trap 1 water in this position. Here we have 1 minus 2, that's going to be negative, so we can't trap any water here. Here we have 2 minus 1, so that's going to be 1, that means we can trap 1 water here. This is 2, so the maximum boundary is 2. Minus 0, that means we can trap 2 units of water here. Next position, we have a 2 minus 1. We can trap 1 water here. Here we have 2 minus 3. That's going to be negative. We can't trap any water here. This is going to be 2 minus 2. Again, 0 water that we can trap here. 2 minus 1. that's 1. So we can trap 1 unit of water here. Here we're going to get 1 minus 2. That's negative. Can't trap any water here. Here we have 0 minus 1. That's also negative, so can't trap any water here, and that makes sense. Why would we be able to trap water here when there's no right boundary? But okay, so we have all of our values. We take 1 plus 1 plus 2 plus 1 plus 1, and we get exactly what we expected, right? We get a 6. We can trap 6 units of water here. So this is the solution taking extra linear memory. Okay, so now I'm going to show you the O of 1 memory solution. It's still linear time, big O of n time, but this time we're not going to need any of this extra memory that we just allocated. We're actually going to do this. We're going to do this with 2 pointers. So initially, I'm going to have my left pointer over here. I'm going to have my right pointer here. So the right pointer is going to be all the way at the end of the input array. So we're going to have our 2 pointers initialized. We're also going to have 2 variables, max left and max right, which are going to be keeping track of the maximum left pointer and maximum right pointer so far. So you can see left is initially 0, so the max so far.
So you want to be a software
Far on the left is 0. You can see right is initially 1, so the max on the right so far is 1. So now we are going to have to update our pointer. Now, which pointer are we going to shift? We're going to take the one that has the smaller max value. So right now you can see max left has 0, max right has 1. So we're going to shift the smaller one, which is left. So we're going to take our left pointer and shift it. So now our left pointer is over here. And just FYI, we know that we can't have any water stored on the endpoints, right? On the left and the right positions, we can't have any water because they're endpoints, right? They can't contain any water. But this position technically can have some water. And how are we going to determine that? Well, we're going to take how much water this can contain, right? We're going to take the max left value that we have in our variable right now, right? How come we don't need the right value? Well, I'm going to show you. So this is the part that you kind of need to notice the trick, I guess, right? So we're in this position, right? Now, remember originally we wanted the minimum down here. You can see we wanted the minimum of the max left and max right. Well, we know what the max left is so far, right? The max left is 0, right? That's what's over here. Now, we technically don't know what the max right is, even though this variable says 1. Yes, so far it's 1, but we know that the max right could actually be 3, right? That's what the true max right is of this position, right? Because there's a 3 over here. So why is it that we don't need that value? Because remember, we want the minimum of the max left and the max right. Now, we clearly know that the max left is 0, right? So it's smaller than what's even at this position, right? And we want the minimum of it. So no matter how big this value is, right? Right now it's a 3, it could be a 10, right? It doesn't matter how big it is because we want the max of the left and the right, and we already know that the left is pretty small, right? It's 0. So it doesn't matter what's in all of these values because we know that the max left is our bottleneck, right? Remember, we shifted our left pointer from here to the next position because left was smaller than right. That's why we shifted it. That's how we're able to calculate the water that's trapped in this position without knowing what the max right is. So with that being explained, let's actually go through this so we can get to the code. So what's the amount of water that we can trap over here? It's actually 0 because the max left, which is the value that we need, is 0, right? So 0 minus what the actual height is in this position is 1. We know that's going to be a -1. We don't count -1s, so we're not going to use that. So we're going to say that 0 water can be trapped here. But you can see, look, this is a 1, right? Our left pointer is here, so we can actually update this. We can cross the 0 out. Max left is now actually going to be 1. So now we're actually at a dilemma, right? Because take a look, our max left and our max right are both 1, so it doesn't really matter which one we shift. Let's just shift the left one again. So we're shifting our left pointer over here now, right? And since they're equal, this is going to be the bottleneck, which is left pointer and the max left, and it's 1 so far. So no matter how big anything over here is, we know that 1 is going to be the bottleneck. We're going to do 1, which is the max left pointer, or the minimum of the max of the left and right pointers, right? So we're going to take that 1 minus the value that's in this position, the height of the index I, which is 0. So that's going to give us a water level that is 1. So that means in this position, we can store 1 block of water. So basically, hey everyone, welcome. Is 1, so we don't update our minus the value that's in this position, the height of the index I, which is 0. So that's going to give us a water level that is 1. So that means in this position, we can store 1 block of water. So basically, I'm running through the algorithm with 2 pointers. So I'm just going to quickly go through the rest of what this example would be. So again, we're going to shift our left pointer because left and right are equal, so it doesn't matter which one we shift. We're shifting the left one over here. So now, to calculate how much water would be stored here, we're going to take the max left pointer, which is 1, and subtract from it the height that's in this position, 2. That's clearly -1, so what we're going to say is that 0 water could be stored here. And so since we reached a height of 2, that means we can update max left and set it to 2 now. So now remember, we want to shift the minimum pointer, and right now the minimum pointer is the right pointer, which is a max height of 1. So we're going to take our right pointer and shift it. And since we shifted the right pointer, now we have to calculate the height or the water that we can contain in this position, right? And so remember, now the bottleneck, right, is going to be this. The max right height for this position is 1, right? So it doesn't matter how big heights over here are, right? There's a 3 here, but we don't care about that because the max right height is 1. And remember, we're taking the minimum of the max left and right height. So no matter what we do, that's always going to be 1 for this position. So we're going to take 1 minus the height in this position, which is 2. That's obviously going to be negative, so we don't have any water here. So we can say 0 water here. And since this is a 2, that means we can also update our max right height now to 2. So this is going to be set to 2 now. The max right height is 2. And since they're now once again equal, they're both set to 2, I'm going to be updating the left pointer because it doesn't really matter which one we do. Okay, so let's calculate the water in this position. So we're at a left position, so we're going to take the max left height, which is 2, minus the height in this position, 1. That's going to give us a 1, meaning that we can contain 1 unit of water. And the height in this position is 1, so we don't update our max left height, but we can now shift our left pointer 1 more position. Now our left pointer is over here. Our max left height stayed the same. It's 2, so let's compute the water we can store here. 2, which is, the boundary. subtracted by the level here, which is 0. So that's going to give us 2 units of water that we can store here. So a 2 here, and let's shift our left pointer again because the max left and rights are equal. So now we're over here. What's the max left? It's still 2 minus the height in this position, which is 1. That's going to give us a 1. So that means 1 unit of water can be stored here. Let's shift our left pointer again. Awesome. So now our left pointer is actually at a 3. So what we're going to do is 2, which is the max left height, minus 3, which is the height in this position. That's going to give us a negative, right? So what that tells us is that we can't store any water here. That's a 0, right? But you can see our max left height can actually be updated now, right? It's going to be set to 3 now. So this is a little bit messy, but let's just say our max left height is 3. Right, and our max right height is still 2. Remember, we're shifting the minimum height. So we're taking now the right height and shifting it. So now we can take, so we're at a right position. We can take the max right, which is 2, subtract it from the height in this position. 2 minus 1 is going to give us a 1. That means we can store 1 unit of water here. Now let's shift our right pointer again because 2 is less than 3. So now we're basically at the last position, right? So the max right height is 2. The height in this position is 2, so what we're going to do is 2 minus 2, that's going to be 0, right? So we can't store any water here. That's going to be a 0. And now you can see we filled in the water levels that we wanted, right? When you take this 1 plus 1